Laplace transforms is probably the first time in a long time that you just had to take a leap of faith with your professor when they're like, blah, 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 blah. It moves stuff from the time domain to the frequency domain, and you're like, sure, why not? But why are you so skeptical? Skeptical? Because at some point you had a professor or a teacher or somebody that was like, I'm going to do this magic sign, and it's going to go like this, and it's going to turn it into a 3. And you're like, sure, why not? And then at some point they said, well, maybe it's a plus or minus 3. And then you just continue to accept it because that's what we do. Well, a Laplace transform is just a function. It's just like a square root or like a squared or like a log. Just like you can log both sides of an equation, you can Laplace both sides of an equation. And it just looks like this. So basically what the Laplace transformation will do is, say you have something like this. You've got a sine function. It'll be like sine of omega t. All right? So basically what it's going to do is it's going to turn it into something that looks like this. So you don't have t's anymore. All you have are omegas, and that allows you to look at it without t getting in the way. So instead you have things that are in terms of s, or the frequency domain. So basically it's a way of taking stuff that is, well, I can't have a better way to say it than to say it's in the that you have time and frequency and you're looking at this, so it's kind of hard to tell from looking at that what the frequency is without measuring it, and that you're going to turn it into something where you can just glance at it and you've got everything you need to know without having to worry about t, because it's kind of repetitive anyway. So the idea is that we're taking something that's in the time domain and we're converting it to the frequency domain, because eventually you just have to trust me, it's going to make your life better. So that's probably not the best way to start the video, just saying just trust me, it'll be fine. But honestly, it's really hard to convince people why Laplace transforms matter until you start getting into applications, and all of a sudden they go, this is amazing, it's like the best thing that's ever happened to me in a math class since the beginning of the semester lately. And so there you go. All right, so the Laplace transform, just like a square root function, except it doesn't take the square root, it takes the Laplace. So if I say I'm going to take the Laplace of some function that's in terms of time, we usually have the standard where we'll write it then as a capital F in terms of s. So if I'm taking the Laplace transform of g of t, then I would say it was capital G of s, but that's not really important. It's just a little bit of a note on the side. Now the Laplace transform is formally defined as an integral that goes from 0 to infinity, e to the minus st, function of t, dt. So you can find the Laplace transform of anything by applying this integral, which is all well and good, except the fact that you get really tired of applying integrals over and over, but eventually you'll see some patterns and we'll take note of that. So for the moment, let's just see if we can find the Laplace of some relatively simple terms. So let's find the Laplace transform of the number 1. Okay? So if I want to find the Laplace transform of the number 1, I go integral from 0 to infinity, e to the minus st, and then my function of t here is actually just the number 1, dt. So I can integrate that because I'm kind of awesome at integration, and that's going to be e to the minus st evaluated from infinity, or 0 to infinity. So minus 1 to the s, and I'm just going to write this out a little weird because it helps me see it better. So I'm going to evaluate this at st, evaluated at t going to infinity, minus 1 over e to the st, evaluated at t going to 0, or t being equal to 0. And that just makes it a little bit easier for me to see what's going on. So I have minus 1 over s. As t goes to infinity on this side, I've got 1 over a supergiant number, which is going to come out to mean 0. And then e to the 0 is just 1, so 0 minus 1. So I have negative 1 over s times negative 1, or just 1 over s. Now, something you're going to be careful about when you're doing Laplace transforms is your s's and your 5's are going to start looking the same. So it's pretty easy to start making mistakes and problems because of just bad handwriting. All right, but what we can do now is, now that we have this, we can say formally that 1 transforms to 1 over s. Okay, so usually what you'll have is, somewhere in the world, you'll have this table of Laplace transforms, and it'll say something like f of t and Laplace s. So you'll see something be like 1 and 1 over s. Now the reason that we have little tables like this is because there's actually a connection. What's really neat is because we have, whatever you call these things, because they're integrals, that means if I now want to find the Laplace transform of, say, the number 6, okay, well, I'm going to do 0 to infinity, e to the minus st, and my function is 6 dt. Now I can pull the 6 out, right, because it's an integral, so that just leaves me with e to the minus st dt. But I've already figured out that that's equal to 6 times that this part right here is the same thing as what I had originally. So that's just equal to not negative, but equal to 1 over s. So there's something called a linearity property with Laplace transforms that says that I can make linear combinations, or not just linear combinations, but yeah, of Laplace transforms, and I can basically break them out. So I don't have to separately find the Laplace transforms of 5, 6, 7, 8, and 10 billion, because it's just going to be 5, 6, 7, 8, and 10 billion times the Laplace transform of 1, which is just 1 over s. So I guess a fancy pants way to say this would be 6 times the Laplace transform of 1, which would be 6 times 1 over s, and you get the same thing. So basically the idea is we're going to come up with some of the really kind of standard Laplace transforms so that we can figure out all the rest of them later. Excellent, so we're going to keep adding to that table. So now let's say that we want to find the Laplace transform of another simple one. Let's say we want to go to the Laplace transform of just the function t. Okay. Now ideally you should pause the video and try to do this on your own and see how far that you can get, because it's good for the soul. Now I can't pull the t out because the t is a function dt, so I'm dt'ing it, so I can't just pull this out. What I end up having to do is a U-substitution, or integration by parts, integration by parts. So I've got du, dt, dv is e to the minus st, dt, so uv, kind of write this in a funny order, uv t e to the st evaluated from there, minus the integral 1 over s e to the st dt from 0 to infinity. So I've got negative 1 over s times, I'm going to do that thingy again. So I have e to the st, evaluate as t goes to infinity, minus t over e to the st as t goes to 0, or when t equals 0, and then plus 1 over s, integral e to the minus st dt, just like that. Excellent. Okay. Now, as for this guy, as you're looking at this, you might say, well, that's infinity or infinity. What do I do? Hopefully you've had enough calculus to know what L'Hopital's rule is. So L'Hopital's rule means if I'm taking the limit as something goes to infinity, and it ends up being infinity over infinity or 0 over 0, then that's the same thing as taking the limit as t goes to infinity of the derivatives of each of those. So the derivative of each of those would be 1 over s e to the st. Now as t goes to infinity, it's going to go to 0 because it's 1 divided by a huge number, so that just goes to 0. Okay, so this goes to 0. And obviously I hate using that word. That goes to 0 too, because the t is 0, and on the bottom I have 1, so 0 divided by 1 is 0. Which is nice, because that just leaves me with the 1 over s term. Now, I have e to the minus st dt. That's the Laplace transform of 1. And that's just something that theoretically you should be able to recognize, or you can just scroll up. There we go. And see that it's right there. Woo. So there we go. So that's the Laplace transform of 1, which I knew is just 1 over s. So it's 1 over s squared. So I can say, adding to my table, that the Laplace transform of t is 1 over s squared. Now you may say, does this continue on? Is t squared equal to s cubed, and so on and so forth? The answer is not 100% exactly, sort of, so no. But I can tell you that if I have t to the n in general, that, let me make this bigger because it's harder to write. It's harder to write little. So if I have t to the n, that the Laplace transform of t to the n is n factorial over s to the n plus 1. So that kind of matches what you see here. So in this first case, we had n would be equal to 0. So we had 1 over s to the first. In this case, n was equal to 1. So we had 1 factorial, which is just 1 over s 1 plus 1 is 2, and so on and so forth. So this does match, can't quite see what it's doing, it does match our pattern, but I don't want to keep doing this forever and ever, so we'll kind of stick it to that one. We will do one more though, and I'll make a separate video for doing something else, because the something else is a whole lot crazier. So now let's just do a Laplace transformation of, because this is a biggie, this one's a really big important one. So let's do a Laplace transform of e to the at, like that. Excellent? Okay. So again, try to do this on your own now that you had a little bit of experience. And I am going to have to say that we're going to assume that a is less than s. This is something that's going to be important later. So 0 to infinity, e to the minus st, e to the at, dt. 0 to infinity, e to the a minus s, t, dt. 1 over a minus s, e, a minus s, t, evaluated from 0 to infinity. Okay, so if I've assumed that a is less than s, then this here is a negative number. So that's okay. Okay? So since that's a negative number, I can write it as kind of what I've been doing before. It's going to be on the bottom. E, a minus s, so that's a negative, well, now I would be s minus a is a positive number, so how do I want to do this so that it makes sense? How about we just say it's a negative number? We'll call it that. 1 over e to the negative, or now it's going to be positive on the bottom, positive number t, because it's not going to matter, minus e to the positive number t. First of all, evaluated as t goes to infinity, and then evaluated as t goes to 0. Okay? So we have 1 over a minus s. Now as t goes to infinity, we have 1 over a really, really big number, so that goes to 0. And then e to the 0 is 1, so 0 minus 1. So that gives us 1s minus a. Okay, so that was a little weird on the notation just because I hate getting caught up in notation and not able to actually do math. So now we can add to our lovely table that says that if I have e to the at, that is always going to transfer over to s minus a, again assuming that s is greater than a. So there's a restriction on that, but aside from that, we're in good shape. So it's kind of a basic introduction to Laplace transforms. Doing some of the more complicated Laplace transforms takes more effort, so we're definitely going to save that for another video.